So let me take you through a step-by-step guide to drawing reaction mechanism using our third example of polar reaction, which is the synthesis of the painkiller paracetamol from 4-aminophenol and acetic anhydride. As you know, paracetamol is a painkiller. It is an active ingredient in many painkiller formulations, such as Panadol. So what this is telling you, the chemistry you've learned so far, the organic chemistry you've learned so far, is good enough to see how useful molecules such as paracetamol are synthesized. I want you to be encouraged. The time and effort you put in your studies is not going to be wasted. The knowledge and skill you will acquire during your studies is going to give you the knowledge and skills required to synthesize, to design useful molecules, drugs such as Panadol. What I'm going to do is take you step by step how Panadol is synthesized from 4-aminophenol and acetic anhydride. So we are going to go through this reaction step by step. When 4-aminophenol and acetic anhydride react, we get N4-hydroxyphenyl acetamide, otherwise known with its commercial name paracetamol. And then as we synthesize paracetamol, there will be a side product that's going to be formed. The side product is acetic acid. We are going to use this reaction as an example and go through a step-by-step guide to drawing reaction mechanisms. So the first step in reaction mechanism is the examination of the reactants and product, so that you can tell what happened to the reactants as the products are formed. Step 1 is examining the reactants and products and assess what happened in the course of the reaction. So let's look at this reaction. This is the reaction scheme. The reaction of 4-aminophenol with acetic anhydride to give paracetamol and acetic acid. So when these two react, these ones are formed. These products are the results of the reaction of 4-aminophenol and acetic anhydride. So when you examine the reaction, the whole purpose is to see what happens to the reactants as the product are formed. So you can use whatever code so that you can locate the reactants in the products. So in this case, what I did, I used green as the code, as the color code for 4-aminophenol. Then I used two different codes for acetic anhydride. This part red and the other one purple. And then I used the same codes in the products, so that you can see that this one, this part of the product is this one, while this other part of the product is this one. And then this part of the product is this one. And then this part of the product, this hydrogen, is basically this one. In reaction mechanism is basically figuring out how bonds are broken and how bonds are formed, and then showing that using curved or curly arrows. Before you do that, you must have a good understanding of the reaction. So the first and most important of reaction mechanism is locating the reactants in the product. You locate the reactants in the product. So what I did, as I told you, this part of the product is from this. So I traced it, okay? So this one, is basically this. I want you to take your time, trace the reactants in the product. So this one is from here, from the 4-aminophenol. And then the other part of the product, this one, as you can see, is from here. We are done with paracetamol. So the side product, acetic acid, this part of acetic acid, as you can see, is from this part of acetic anhydride. So part of the acetic anhydride is given as acetic acid. The other part of acetic anhydride is in the product. This is from acetic anhydride, and then this part of our product is the other part of acetic anhydride. Then this one is basically this. Okay, so this is what you should do first. Locate the reactants in the product, and then this is going to provide you with a lot of useful information. After you have done this, the next thing you need to know is, we want to know the new bonds that are formed and the old bonds that are broken. Okay, what are the new bonds that have been formed and what bonds have been broken? And then this you can easily tell from the trace. So here, this is from this one and this is from this. So as a result, in here initially you had a bond between this nitrogen and hydrogen, but now we have a bond between this nitrogen and this carbonyl carbon. So this is one of the new bonds that is formed, this one. The other new bond that is formed is between this oxygen and this hydrogen, between this one and this one. So we've managed to identify the new bonds that have been formed. As you can see how useful it is to locate the reactants in the product. Whatever means you have, code the reactants and then you translate the same codes in the product. You can even trace them the way I did. When you do that, you will know the new bonds that have been formed. So this is one of the new bonds that is formed. This is the other bond that is formed. You can also tell the bonds that are broken. So for a bond between this nitrogen and that carbonyl carbon to form, the bond between this nitrogen and hydrogen, this particular bond has to break. So that's one of the bond that is broken. The other bond that is broken, so this one, it came and attached itself here. When it did that, it separated itself from the other part of the acetic anhydride. So the other bond that is broken is this one. These are the new bonds that have been formed and the old bonds that have been broken. This we manage to easily identify because we located the reactants in the product. We traced the reactants in the product. Then when you do that, it will clearly show you the new bonds that are formed and the old bonds that are broken. So this is very, very important. The other thing, this thing is going to locating the reactant in the product. It's going to tell us, it's also going to tell us what type of reaction this is. As you can see, what happened in this when this product is formed, this part of the acetic anhydride substituted this hydrogen of 4-aminophenol, while this part of acetic anhydride substituted this part of the 4-aminophenol. So as a result, this reaction is a substitution reaction. So examining the reactant and the product is the first step and most important step in drawing reaction mechanism, as it will help you identify the bonds that have been broken and the bonds that have been formed. After this, now you know which bonds are broken and which ones are formed. After this, in the reaction mechanism, now you figure out how these bonds are formed and broken. What we know clearly, there is a bond that is formed between this nitrogen and carbon, between this nitrogen and carbon, between this nitrogen and this carbon, there is a bond that is formed. Now we have to figure out how this bond is formed. So what we need to do, since this is a polar reaction is between oppositely charged species. A polar reaction is between a nucleophile and an electrophile. So in the next step, we must identify which of the two must have acted as the nucleophile. All we know, there is a bond that is formed between this nitrogen and this carbon, between this nitrogen and this carbon. To form the bond between this nitrogen and this carbon, which one of these? Is it the 4-aminophenol, or is it the acetic anhydride that acted as the nucleophile? Then if you can identify the nucleophile, and then the other one will be the electrophile. So this step is very, very important. I don't want you to waste your time drawing arrows which will take you nowhere. So once we have identified this, once we have located the reactants in the product, once we have clearly identified the bonds that are broken and the bonds that are formed, now we know where to take these curly arrows to, from this one to the other one, towards the formation of this bond. So with this information, the next step is to determine which of the two reactants is the nucleophile and then which one is the electrophile. So in step 1, we have identified the new bonds that are formed. We have also identified which atoms of 4-aminophenol and acetic anhydride have bonded with one another. The next step is to determine which of the two is going to be the nucleophile and which one is going to be the electron. Is it 4-aminophenol which is the nucleophile, or acetic anhydride, and vice versa? That's what we need to do. So in order to do that, we have to determine the polarization patterns of the different functional groups in 4-aminophenol and acetic anhydride. So the next step is to identify the nucleophilic and electrophilic centers in the reactants based on the polarization pattern of the different bonds, the functional groups in 4-aminophenol and acetic anhydride. We determine the polarization patterns of the different functional groups in 4-aminophenol and acetic anhydride. You remember this we discussed in the previous lecture when you looked at how to determine the polarization pattern of functional groups, of different functional groups. Polarization pattern is dependent on the polarization of a bond. If you have a bond between two atoms and these two atoms are not the same, when one is more electronegative than the other, the more electronegative atom will attract the electrons of the bond towards itself, making it electron rich, the other one being electron deficient. So what we need to do next is to look at these two molecules, 4-aminophenol and acetic anhydride, the polarization patterns of the different polarized bonds in these molecules. So we have one here, we have a polarized bond in here, we have a polarized bond in here. This is not polarized because this is a bond between carbons. This is a benzene ring. This is a bond between carbons, and carbon and hydrogen. As we know, such type of bonds are not polarized. So this is not a polarized bond. However, this one is a polarized bond. This one is a polarized bond. We have to determine the polarization pattern to determine which one is electron rich and which one is electron deficient. Similarly, we come in here. In here, we have a carbonyl carbon here, oxygen here, another carbonyl carbon, and an oxygen here. Okay, so this bond is between carbon and oxygen. This bond is another polarized bond between carbon and oxygen. This is also a bond between carbon and oxygen. So these are the polarized bonds. So based on the electronegative difference between the atoms involved in this polarized bond, we determine their polarization pattern. We determine the electron rich and the electron deficient centers in this. This by now you should be conversant with, you should be familiar with, we should have the expertise in determining the polarization patterns of different bonds. So I'll just put the results of the analysis. For example, in here we have a bond between nitrogen and hydrogen. Okay, nitrogen and hydrogen. As you know, nitrogen is the third most electronegative element. So nitrogen is more electronegative than hydrogen. So nitrogen will pull the electrons of this bond towards itself. That's why on the nitrogen we have partially negative charge. On the hydrogen we have partially positive charge. The other polarized bond is between this oxygen and this hydrogen. In here you see, since oxygen is more electronegative than hydrogen, remember oxygen is the second most electronegative element in the periodic table. So this bond between the oxygen and hydrogen is very polarized. Since oxygen is more electronegative than hydrogen, the oxygen withdraws, pulls the electrons of this bond towards itself. As a result, on this oxygen we have excess of electrons, on the other one we have deficiency of electrons. So what we have to do is analyze the polarization patterns of the different bonds. So this is how it is. In here we have a bond, a polarized bond between this carbon and oxygen. This carbon and oxygen, again oxygen is more electronegative, so the electrons of this bond will be pulled towards the oxygen. This, as a result, this carbon will be electron deficient while the oxygen will be electron rich. Okay, similarly we have a bond in here between carbon and oxygen. Oxygen is more electronegative than carbon, so on this oxygen will have excess of electrons. So this is how we determine the polarization patterns of the bond. The purpose of doing this is to identify. We know from step 1 there is a bond that is formed between this nitrogen and that carbon. Okay, between this nitrogen and that carbon. That's what we know from step 1. So when a bond is formed between this nitrogen and this carbon, which one of them acted as the nucleophile? Is it 4-aminophenol or is it acetic anhydride that acted as the nucleophile? So that's why we need to identify the nucleophilic and electrophilic centers of the different functional groups in the reacting species for purpose of determining which one of the reactants is going to act the nucleophile and which one is going to act the electrophile. So since from step 1 there is a bond that is formed between this nitrogen and this carbon, when you look at this nitrogen has excess of electrons, this carbon has got deficiency of electrons. So in the reaction between 4-aminophenol and acetic anhydride, it is 4-aminophenol that acted as the nucleophile, and then it is acetic anhydride that acted as the electrophile. So this, using this analysis and assessment from step 1, we determine which of the reactants is going to be the nucleophile and which one is going to be the electrophile in the reaction. Okay, so this analysis will tell us this one is going to be the nucleophile while this one is going to be the electrophile. So in the reaction between 4-aminophenol and acetic anhydride to give paracetamol and acetic acid, it is 4-aminophenol that acted as the nucleophile while acetic anhydride acted as the electrophile. Again, of course, the bond is between this nitrogen and this carbon. Okay, so in the reaction between 4-aminophenol and acetic anhydride, it is this nitrogen which is the nucleophilic center, and then it is this carbonyl carbon which is the electron deficient center. Okay, so the reaction is going to be between this nitrogen and this carbon. So what we know in this reaction, we know the product. When you react 4-aminophenol and acetic anhydride, you get paracetamol and acetic acid. By assessing how the reactants reacted to give the product in step 1. We have determined the bond formation is between this one and this one. Therefore, this will be the nucleophile and this will be the electrophile. Straightforward. But what if we did not know the product of the reaction of 4-aminophenol and acetic anhydride? Suppose I did not give you what the product of the reaction between 4-aminophenol and acetic anhydride is. How are you going to predict the product? How are you going to know what product is formed when 4-aminophenol and acetic anhydride react with one another? Okay, this is a situation which you are normally confronted with as an organic chemist. You have two reactants. You don't know what product is formed, but you have to know what product is formed. So in these molecules, we have to determine the most electron-rich and the most electron-deficient centers. We have to determine the most nucleophilic and the most electrophilic centers in the reacting species, because at the end of the day, the reaction is going to be between these most electrophilic and most nucleophilic centers, because the reaction is going to be driven by the Coulombic force of attraction. As you remember, the Coulomb's law says the force of attraction between oppositely charged species is directly proportional to the charges. So the more nucleophilic center will have more negative charge, and the most electrophilic center will have more positive charge. So when these two reacting species come close to one another, there is going to be a force of attraction. The force of attraction will be strong between the two centers, between the most electrophilic center in one of the reactant and the most nucleophilic center in the other reactant, and then the two attract to each other, and then a bond is formed. So even when you don't know what the product of a reaction is, understanding how bonds are polarized and comparing the nucleophilicities and electrophilicity of different polarized bond, you can easily predict what kind of bond is going to be formed. So let's look at this one. In here, on 4-aminophenol, we have two nucleophilic centers, this nitrogen and this oxygen. Between the nitrogen and the oxygen, which one is more nucleophilic? Fortunately for us, acetic anhydride is a symmetrical molecule. If I put a line like this, or if I put a mirror here, you will see that this side of acetic anhydride and this side of acetic anhydride is the same. So either of them, either this carbonyl carbon or that carbonyl carbon, can act as the electrophile. The product we are going to get will be the same. It does not matter. But when you have a situation where we have two different types of electrophilic centers, you must determine which of them is going to be more electrophilic. Everything is going to be dependent on the polarization of the bond. The more polarized the bond is, the more electrophilic and nucleophilic centers you will have on that particular bond. So which of these is more nucleophilic? In the case of acetic anhydride, it does not matter. We can choose this one to be the electrophilic center. We can also choose this one, the electrophilic center. The product we are going to get will be the same. But in here, if you choose this one to be the nucleophilic center, there is going to be a bond that's going to form between this oxygen and that carbon. If you choose this one to be the nucleophile, the reaction is going to be between this nitrogen and the carbonyl carbon. But the product is going to be one. Is the product the one that results from bond formation between this oxygen and this carbon, or is it the one that results from bond formation between this nitrogen and that carbon? In order to do that, we have to determine which of these is more nucleophilic. Is it nitrogen which is more nucleophilic, or is it oxygen? We have to determine that. If you look at, oxygen is more electronegative than nitrogen. Therefore, you might think this oxygen must be more nucleophilic than nitrogen. But that's not the case. If that was the case, water would have been more basic than ammonia. The reason why ammonia is basic, ammonia can use its lone pair of electrons and pick a hydrogen from an acid. That's why it is more basic than water. Water cannot easily pick a hydrogen from an acid. That's why ammonia is very basic while water is neutral. If you compare ammonia and water, the difference between ammonia and water in the nitrogen and oxygen. In ammonia we have nitrogen and 3 hydrogens. In water we have oxygen and 2 hydrogens. The hydrogens are constant between them. What is different between them? In the case of water we have oxygen. In the case of ammonia we have nitrogen. What made ammonia to be more basic than oxygen is the nitrogen. Nitrogen is a better electron donating group than oxygen. Oxygen, since it is more electronegative than nitrogen, it holds on to its electrons tightly. It does not give its electrons to be used to form a bond with another element. However, nitrogen is an electronegative element, but more willing to donate its electrons to be used to form a bond with another element. That's why ammonia is much more basic than water. You can drink water without any problem. The water, it can go into our body. It's not going to do any damage. The water is not going to react with the chemical compounds in our body because it is a very weak nucleophile. But if you take ammonia, I know you are going to be in a lot of trouble. The reason being, the nitrogen of ammonia is very nucleophilic. As a result, it goes into our body and react with many electrophilic centers in our body, changing the chemical compositions of the compounds that are in our body. So what I'm saying is that nitrogen is more nucleophilic than oxygen. So when we don't know the products of the reaction between two reacting species, it is possible for us to predict what the product is going to be. That's why understanding mechanisms is very, very important. Even when you don't know the product of a reaction, you can easily predict what the product is going to be if you analyze the reacting species and determine their most nucleophilic and their most electrophilic centers. For sure, the bond formation is going to be between the most nucleophilic and the most electrophilic centers in the two reacting species. So that's what this thing is saying. If the product of the reaction is not known, if you don't know what the product of the reaction between two reactants is, if the product of the reaction is not known, identify the most nucleophilic and electrophilic centers. So you identify the most nucleophilic and the most electrophilic centers in this reacting species. And then the reaction is going to be between those most nucleophilic and most electrophilic centers. So understanding mechanism is a powerful tool. Knowing reaction mechanism is a powerful tool. You can even predict the product of reactions you have never come across with, because the bond between this reacting species is going to form between the most nucleophilic and the most electrophilic centers. So now, coming back to our reaction, in this particular case, we now know this is the nucleophile and this one is the electrophile. So since these are oppositely charged species, they will attract to one another based on the Coulombic force of attraction. In order for them to form a bond, they attract each other and come close to a bonding distance. So the next step is to position the nucleophilic and electrophilic centers within bonding distance in the way they appear in the product. We now know this is the nucleophile. And this is the electrophile. And then there's going to be a bond between this nitrogen and this carbon. The third step is about positioning the nucleophilic and electrophilic centers within bonding distance, just the way they appear in the product. So you look at the product. In the product, we have a bond that is formed between this nitrogen and that carbon. You open up that bond so that you can easily position the nucleophile and the electrophile in a bonding distance. So after this, what you are left with is to push electrons from the nucleophile to the electrophile in order to form a bond. So we have now identified the nucleophile and the electrophile. We know what the nucleophilic center is, and we also know what the electrophilic center is. We have also brought them to a bonding distance. The only thing that is left in step 4 is to draw a curly arrow from the nucleophile to the electrophile. So the fourth step is drawing a curly arrow from the nucleophile to the electrophile. So in this curly arrow, we are going to use an arrow which is double-headed, showing the movement of 2 electrons. The tail of the arrow is going to start from the source of the electrons, the nucleophile, the lone pair of electrons on the nitrogen, and then it will be pointing towards the electrophilic center, which is the carbonyl carbon. So the tail will be on the nitrogen, which is the nucleophile, and then the head of the arrow will be on the carbonyl carbon, which is the electrophile. We draw an arrow from the lone pair of electrons on the nitrogen towards the carbonyl carbon, like that. So this is how we draw curly arrow from the lone pair of electrons on the nitrogen towards the carbonyl carbon. So the nucleophile, the nitrogen, this nitrogen, on 4-aminophenol, it will donate a pair of electrons to form a bond with the electrophilic carbon on acetic anhydride. So both electrons required for bond formation between this nitrogen and this carbon are going to be provided by the nitrogen. The electrons that are required for bond formation between the nitrogen and the carbon are provided by the lone pair of electrons on the nitrogen. So these 2 electrons will now be used to form a bond with this carbon. So a bond between 2 atoms, for example, in this case between this nitrogen and this carbon, is because of electrons. So when you have a bond between this nitrogen and that carbon, what's going to hold this nitrogen and this carbon together are the electrons. So in this case, the electrons that are required for bond formation between the nitrogen and the carbon are provided by the nitrogen. This lone pair of electrons on the nitrogen, they are the ones that are going to be used to form a bond with the carbon. So a bond between 2 atoms is due to a pair of electrons between these atoms. Both electrons in this particular case required to form a bond between the nitrogen and the carbon are provided by the nitrogen. It is the electrons, the lone pair of electrons on the nitrogen, that are going to be used to form a bond with the nitrogen. So now we can see a product that's going to be formed as a result of bond formation between this nitrogen and the carbon. So we have so far gone through 4 step-by-step guides to drawing reaction mechanisms. So what we have achieved so far, we have identified the nucleophile and the electrophile, and we have positioned the nucleophile and the electrophile in a bonding distance where they can easily form a bond with one another. Then we have identified the nucleophile is 4-aminophenol, the electrophile is acetic anhydride. We have identified the nucleophilic center on 4-aminophenol is the nitrogen, and the electrophilic center on acetic anhydride is the carbonyl carbon. So since the nitrogen is a nucleophile, the carbonyl carbon is an electrophile, they are going to have a Coulombic force of attraction between them so that they become to a bonding distance. When they come to a bonding distance, electrons are going to flow from the nucleophile to the electrophile, from the lone pair of electrons on the nitrogen of the nucleophile towards the carbonyl carbon of acetic anhydride. So when such happens, electron will flow from here to here, and then these electrons now will be used to form a bond with this carbon, with the carbonyl carbon. So in this step, the fifth step is about drawing the structure of the product as indicated by the curly arrow. The curly arrow indicate to us we should draw a bond between this nitrogen and the carbonyl carbon. So this is the product that is formed. When a bond is formed between this nitrogen and this carbon, this is the product that is suggested or that's indicated by the curly arrow. And then the electrons of this bond, the one I have shown in green, are the electrons that were originally the lone pair of electrons on the nitrogen. So these electrons were the ones that were originally the lone pair of electrons on the nitrogen. So the electrons of this bond were the lone pair of electrons on the nitrogen, the nucleophile. It is the nucleophile that provides both electrons required to form a bond with the electrophile. So after the bond is formed, we have this product. Let's analyze this product. You'll see that this carbon has a problem. Can you tell me what the problem with this carbon is? If you look at this carbon, how many bonds do you see on that carbon? You see 2 bonds as a result of the double bond. 2, 3, 4, 5 bonds. Each of these bonds bringing 2 electrons, isn't it? As a result, on this carbon we have how many electrons? 10 electrons. Is it allowed to have 10 electrons on a carbon? No. Carbon is tetravalent. Carbon, in order to be stable, it needs 8 electrons to be stable. Since this carbon has 10 electrons, it has violated the octet rule, which is not allowed. So if you look at this carbon, it has got 5 bonds, and 5 bonds implying 10 electrons on the carbon, violating the octet rule. So this is not allowed. So in order not to violate the octet rule, we have this step 6 as a guide. This step 6 as a guide says, when forming a bond, when a nucleophile forms a bond with an electrophile, and when you draw the structure, make sure to avoid drawing a bond that violates the octet rule. So since this has violated the octet rule, we must do something about it. And that's what we are going to see next. What we need to do to avoid breaking the octet rule as a bond is formed between the nucleophile and the electrophile. So when a nucleophile attacks an electrophile and forms a bond with it, what happens next will depend on the nature of the electrophile so as to not violate the octet rule. So it will depend on the nature of the electrophile. So what happens next will depend whether it is positively charged or partially positively charged. Then when it is partially positively charged, it also depends whether this electrophile is bonded through a double bond, as in the case of acetic anhydride, or through a single bond. So what we are going to see, what happens, the 3 scenarios. The first scenario is when this is positive. The other scenario is when it is partially positive. When it's partially positive, there are 2 possibilities. It could be involved in a double bond or a single bond. So what the next step of the reaction will be when a nucleophile attacks a carbonyl will depend on the nature of the electrophile. So we are going to see the three scenarios. So the first scenario A, we are going to look at is when the electrophile is positively charged. So in this case, the nucleophile donates both electrons of an electron pair to form the bond. Then the electrophile accepts both electrons, forming the bond, fulfilling the octets of the electrophile. So we have the electrophile is fully positively charged. So as a result, this electrophile does not have octet of electrons. For example, if it is a carbocation, it will only have 6 electrons in its valence shell. It does not have octet of electrons. So when a nucleophile attacks such type of electrophiles, the electrophile will just accept the electrons of the bond. When it accepts the electrons of this bond, the electrophile will have octet of electrons. Nothing will happen. The electrophile, since it does not have octet of electrons, it will happily accept these 2 electrons from the nucleophile in order to fulfill its octet of electrons. Let me give you an example. You take a carbocation. This carbocation has 1, 2, 3, 4, 5, 6 electrons. So it is a positively charged, a fully positively charged electrophile. So when it reacts with a nucleophile, like a hydroxide ion, HO-, the HO-, the nucleophile, will donate its 2 electrons to form a bond with the carbon. So now, when these 2 electrons are used to form a bond with this carbon, the carbon will end up having 8 electrons. So when a nucleophile attacks a positively charged electrophile, like a carbocation, the electrons of the nucleophile will be used to fulfill the octet of the electrons. So the electrophile will accept the electrons of the bond. So this is the scenario when you have an electrophile that is positively charged. You remember the electrophile we have in acetic anhydride is not fully positively charged. This will not apply for our case, but there are possibilities when you work on a mechanism. You can have an intermediate that is positively charged. Okay? So when the nucleophile attacks such electrophiles, the electrophile will accept those additional electrons, and those additional electrons will make it happy, as they will make sure it has octet of electrons. So let's look at the other scenarios. The other scenario, a neutral but partially positive atom, and this one is in a single bond. So you have a situation like this. This is partially positive. The electrophile is partially positive. It is bonded with another atom that's more electronegative than it through a single bond. What happens to such type of bonds when a nucleophile attacks such type of electrophiles? So you have this electrophile. This is partially positive. This is partially negative. This molecule is neutral. Remember, this partially positive center and this partially negative center, they cancel out. As a result, this molecule is neutral. But since it is polarized, and since Y is more electronegative than X, X is electrophilic center. X is an electron deficient center, so it can be attacked by a nucleophile. So when you bring a nucleophile to attack this, when a bond is formed between the nucleophile and X, when the nucleophile brings its 2 electrons to form a bond with X, the old bond that was between X and Y must break. If it does not break, the octet of X will be violated. Remember what we have in here? This X has octet of electrons. It could be a carbon having octet of electrons. A carbon bonded to a halogen, for example. It could be, for example, CH3 X. Because of this bond, as well as the 3 bonds with the hydrogen, this carbon has octet of electrons. But it's a polarized bond. It's a partially positive carbon because it is bonded to an electronegative atom like chlorine, for example. So, but it has got octet of electrons. So when a nucleophile brings electrons to form a bond with it, if this bond is not broken and Y goes away with both electrons of the bond, the octet of this X will be violated. So when these nucleophiles form a bond with an electrophile that is bonded through a single bond to another atom, this single bond breaks. When this one forms a bond with it, this bond breaks. So this bond breaks, and then Y goes away with both electrons of the bond. Y becomes negatively charged. So now you have a new bond between the nucleophile and X. X now has octet of electrons, the same as the nucleophile. Okay, so when you have a single bond like this, when a nucleophile attacks the electrophilic center, the original sigma bond, single bond between X and Y breaks. Let me give you an example. So this is a bond between hydrogen and bromine. So this is a polarized bond because bromine is more electronegative than hydrogen. So on bromine we have excess of electrons. On the hydrogen we have deficiency of electrons. The hydrogen is partially positive. The bromine is partially negative. In a reaction with a nucleophile, this HBr is going to behave as an electrophile. Let's look at this hydrogen. In this molecule, there are these 2 electrons between this hydrogen and the bromine. As a result, this hydrogen has got the duet of electrons it needs to become stable like helium, the corresponding noble gas. So when a nucleophile comes and attacks this hydrogen and forms a bond with the hydrogen, this bond has to break. If this bond does not break, on this hydrogen we'll have 4 electrons. So when this nucleophile attacks this electrophile and forms a bond with it, this particular bond has to break so as to not violate the octet of electrons or the duet of electrons on this hydrogen. So you'll have a bond that's going to form between the OH and the hydrogen, and then the bromine will leave with the electrons of this bond becoming negatively charged. So you get a neutral product with duet of electrons. In order for that to happen, this bond has to break. If this hydrogen and this bromine were still bonded, you will see because of this bond there are 2 electrons, and then because of this other bond there are 2 electrons. In total there will be 4 electrons, and hydrogen only forms 1 bond. So as a result, this bond must break. It could be a carbon also. A carbon, for example, this one CH3Br. When the OH forms with this carbon, this bond must break. So when you have a partially positive electrophile that is bonded through a sigma bond, when a nucleophile attacks it, when a nucleophile forms a bond with it, this bond has to break. It has to be accompanied by a breakage of the sigma bond. This is part B, a neutral but positively charged atom that is involved in a single bond. The other partial positive possibility is to have a neutral, partially positive atom that is bonded through a double bond, not a single bond. So this is the next scenario. When you have a polarized pi bonded carbon or pi bonded electrophilic atom. So a situation like this. So we have a bond between X and Y, a double bond between X and Y. The reason why X is partially positive while Y is partially negative is because Y is more electronegative than X. Y pulls the electrons of this bond towards itself, as a result having excess of electrons on Y and deficiency of electrons on X. So in this polarized double bond, this atom is partially positive. So it can easily be attacked by a nucleophile. Now, what happens when a nucleophile attacks such kind of atom? So this is the polarized pi bond when a nucleophile attacks it. So as you can see again in here, both X and Y, their octets is fulfilled. These are neutral, stable molecules. When a nucleophile attacks such an electrophile, when a nucleophile donates its electrons to form a bond with such kind of electrophiles, if nothing happens, the octet of this will be violated. In order not to violate the octet, the pi bond must break. So this will be accompanied by a breakage of a pi bond. So this pi bond will break, and then the electrons of this pi bond will be on Y, the other element, the more electronegative element of the two. The nucleophile will donate both electrons to form a single bond with the electrophilic center, so as to not violate the electron. The pi bond between X and Y breaks. This pi bond breaks with Y, leaving with electrons of the bond, so like that. So at the end of the day, when you look at X, originally it had how many bonds? 2 bonds. In the product, it has got how many bonds? 2 bonds. It has not gained, it has not lost. So it is comfortable. It has got the octet of electrons it needs. In order for it to have octet of electrons, this pi bond must break. If the pi bond does not break, it will have extra or additional electrons, violating the octet rule. So let's look at a scenario for a carbonyl, a carbon-oxygen double bond, which is the case in acetic anhydride. In acetic anhydride, we have a carbon-oxygen double bond, which is a very polarized bond. Since oxygen is more electronegative than carbon, on the oxygen we have excess of electrons, on the carbon we have deficiency of electrons. As a result, this carbon is electrophilic carbon, a very electrophilic carbon that can easily be attacked by a nucleophile which I represent as a nu. So when this nucleophile forms a bond with this, what's going to happen? When this nucleophile forms a bond with it, so as to not violate the octet of the carbon, this bond breaks. Let's look at this carbon before it was attacked. You see this carbon has got how many bonds? 1, 2, 3, 4 bonds. 8 electrons. Octet of electrons. So when this one attacks this and forms a bond with it, the formation of the bond will be accompanied by breakage of the pi bond. So this pi bond breaks to get this product. As you can see, this carbon, just like the original carbon, has got octet of electrons. 1, 2, 3, 4, 5, 6, 7, 8. If this pi bond was not broken, this carbon would have had 10 electrons. In order not to violate the octet rule, this pi bond is broken. When this pi bond is broken, the electrons of this pi bond will go to the electron negative element. So the nucleophile donates both electrons to form a single bond with the electrophilic center X, so as to not violate the octet rule. The pi bond between X and Y breaks, with Y leaving with electrons of the bond. In this case, the X is carbon, the Y is oxygen. So when this bond is formed between the nucleophile and the carbon, so as to not violate the octet rule, this bond breaks. The pi bond breaks. When the pi bond breaks, the electrons of the pi bond will go to the oxygen to give us this product. So these are the 3 scenarios. So when a nucleophile attacks an electrophilic center, when a new bond is formed between the nucleophile and the electrophile, something must happen. What will happen? will depend on the nature of the electrophile. If the electrophile is positively charged, that means it does not have octet of electrons, it will happily accept the electrons that are donated by the nucleophile, becoming neutral. But if you have a neutral molecule in a polarized bond, when the nucleophile attacks the electrophilic center, a bond has to break. If the electrophile is involved in a single bond, only a single bond, when the nucleophile attacks the electrophile, that single bond breaks with the other atom, with the atom that's living going away with the electrons of the bond. However, if this neutral polarized bond is in a double bond, that means if it has a sigma bond and a pi bond, when a nucleophile attacks the electrophilic center, the pi bond breaks. So these are the possibilities. So when you are drawing a reaction mechanism, when a bond is formed, so this is the scenario we have. So when this nucleophile attacks this carbonyl carbon, so as to not violate the octet rule, a bond has to break. So if you look at this, you have between this carbon, the electrophile, and this oxygen, here we have a double bond. On this side, we have a single bond. So when this nucleophile attacks this carbonyl carbon, either the double bond or the single bond will break. There are two possibilities. Which bond is going to break? Is it the sigma bond or the double bond or the pi bond that's going to break? What do you think? Is it this sigma bond or is it the pi bond that's going to break? What do you think? What will determine the breakage of a bond? What will determine whether a bond is going to break easily or not? It's going to depend on its strength. Which bond is strong? A sigma bond or a pi bond? Sigma bonds are much more stronger than pi bond. So when a bond formation to a particular atom causes another bond on that atom to be broken, it breaks the multiple bond instead of the single bond. This is because pi bonds are weaker than sigma bonds. So here we have a multiple bond between this carbon and this oxygen. Then we have a single bond between this carbon and this oxygen. Either this bond or this bond could break, but the one that's going to break will be the weaker bond. So it is this bond that's going to break. So step 7 in our guide to reaction mechanism says, when a bond formation causes another bond to break, the bond that's going to break will be the weaker bond. So if you have a scenario of a pi bond and a sigma bond, since pi bonds are weaker than sigma bond, the bond, when this one forms a bond with it, the bond that's going to break will be the weaker bond, the pi bond. So this pi bond breaks and not the sigma bond. So as a result, the product that's going to form will be this one. So when this one attacks the electrophilic carbonyl carbon of acetic anhydride, when the nitrogen of 4-aminophenol attacks the carbonyl carbon of acetic anhydride, so as to not violate the octet rule of the carbon, a bond has to break. The bond that's going to break is the weakest bond. So between this bond has got sigma bond and pi bond, while this one has got only sigma bond. Sigma bonds, since they are stronger, they cannot break easily. So what's going to break will be this. So we have gone through 7 steps in our step-by-step guide to reaction mechanism, and this is where we have arrived at. When this nucleophile formed a bond with the electrophilic carbonyl carbon in order not to violate its octet of electrons. This double bond that was there between this carbon and the oxygen, it broke with the electrons of the pi bond going to the oxygen. So as you can see, this carbon now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Very happy. So what we saw up to now, what happens to the electrophile so as to not break its octet of electrons. We have not yet considered what happens to the nucleophile. What happens to the nucleophile when it forms a bond with an electrophile? This is what we are going to see next. What happens to the nucleophile when it has formed a bond to the electrophile? Let's just look at this nitrogen. I want you to tell me if you see a violation. Nitrogen forms how many bonds? Nitrogen forms only 3 bonds. Moja, mbili, tatu, only 3 bonds. As in the case of ammonia, the simplest example nitrogen compound we have is ammonia NH3. Nitrogen forms how many bonds? 3 bonds. Nitrogen does not normally happily form 4 bonds. If it forms 4 bonds, something must happen. It cannot remain neutral. The nitrogen in ammonia has got octet of electrons. The 6 electrons of the 8 comes as a result of the 3 bonds nitrogen has with the hydrogens, with the 3 hydrogens, 6 electrons. In order to have octet of electrons, it must have additional electrons. Those additional electrons are the lone pair of electrons on the nitrogen. You remember the 4-aminophenol initially had a lone pair of electrons. But in this product, when it formed a product with carbon, it does not have those lone pair of electrons anymore. Instead, it has got 4 bonds. As you can see, it has got 1, 2, 3, 4, 5, 6, 7, 8 electrons. It has got octet of electrons. But nitrogen does not form 4 bonds. It only forms 3 bonds. So what happens to a nucleophile? Whatever nucleophile, the moment it has formed a bond with an electrophile. So what happens to it is going to depend on the nature of the nucleophile. When a nucleophile forms a bond with an electrophile, what's going to happen to the nucleophile will depend on its nature. Whether it is neutral or negatively charged. Okay, so we'll look at the 2 scenarios. A scenario where we have a neutral nucleophile attacking an electrophile, or a negatively charged nucleophile attacking an electrophile. So let's look at these 2 possibilities. So this one, the first one, we are going to look at the case of a neutral nucleophile attacking an electrophile. So this is a neutral nucleophile. It is not a negatively charged nucleophile. The reason why this is a nucleophile is because it is more electronegative than E. So it has pulled the electrons of this bond towards itself, in the process having excess of electrons. Not only that, it also has lone pair of electrons. So this is a very good neutral nucleophile, and it can donate these electrons to form a bond with an electrophile. So let's see what happens when it does that. So when a neutral nucleophile like this donates its electron pair to form a bond with an electrophile, the nucleophile becomes positively charged. Why? So here, this is a neutral nucleophile. It's reacting with an electrophile. So when this nucleophile forms a bond with the electrophile like this, it's going to use its own electrons to form a bond with the X. In the process, the nucleophile is going to lose electrons. When an atom loses an electron, it becomes positively charged. So this neutral nucleophile, it has used its own electrons to form a bond with the electrophile. When it forms a bond with the electrophile, of course, this bond is going to break. Our focus is not on this. That one is settled. Of course, this one has to break. But this nucleophile, after it has formed a bond with X, it becomes positively charged. It becomes positively charged. So when a neutral nucleophile donates its electron pair to form a bond with an electrophile, it becomes positively charged. It becomes positively charged. Let me give you an example. So this is an amine. So in this amine, you have this amine has got 3 bonds, giving it 6 electrons. Together with lone pair of electrons, it has got 8 electrons. So as you can see, these electrons, they are the belongings of the amine. When this amine uses its electrons to form a bond with this hydrogen, it is basically donating its electrons. When an atom donates its electrons to form a bond with an electrophile, it for sure becomes positively charged. So when a neutral nucleophile donates its electron pair to form a bond with an electrophile, it becomes positively charged. This is another example. This is an alkene. Alkenes are nucleophiles. They are neutral nucleophiles. So the reason why an alkene is nucleophilic is because of the pi bonds. These pi bonds are found above and below the carbon-carbon nuclear axis. The pi bond belongs to both carbons. That's why when we're drawing the arrow, we start from the middle and we use that to form a bond with the hydrogen. So it is possible this carbon could be the one that's forming a bond with this hydrogen. But the other carbon, since it has lost its electrons, it becomes positively charged. So the point is, when a neutral nucleophile forms a bond with an electrophile, this neutral nucleophile becomes positively charged. The nucleophilic center, in the case of 4-aminophenol, it is the nitrogen which is a nucleophilic center. So when the nitrogen forms a bond with the carbonyl carbon of acetic anhydride, when it forms a bond with it, when it uses its electrons to form a bond with the carbonyl carbon, that nitrogen becomes positively charged. Okay, the other scenario is when you have a nucleophile that is negatively charged. So this negatively charged nucleophile, it has got excess of electrons. The reason why it is nucleophilic, it is because it is negatively charged. So it can easily give away this electron that has made it to be negative. When it gives away its electrons, in the process it becomes neutral, happy. When a negatively charged nucleophile attacks an electrophile, this negatively charged nucleophile in the product becomes neutral. When a nucleophile that donates its electron pair to form a bond with an electrophile is negatively charged, after it has formed a bond with the electrophile, the nucleophile becomes neutral. So this nucleophile, which is negatively charged, when it forms a bond with X, when you have a bond that's going to be formed between X, it is this excess electrons that has made this nucleophile to be negatively charged. So when it gives away these electrons, when it shares its electrons, the electrons that has made it to be negatively charged, when it gives away those electrons and forms a bond with an electrophile, it becomes neutral. It becomes a neutral nucleophile. So let me give you an example. So this is hydroxide ion minus OH. This is very highly reactive, nucleophilic. It is very highly reactive because it's negatively charged. It will want to get rid of this negatively charged. So in order to become stable, neutral, it has to get rid of these electrons. Happily it does so, because getting rid of these additional electrons that have made it uncomfortable, okay, will now be shared to form a bond with an electrophile. In the process, it becomes neutral. So when a nucleophile attacks an electrophile, when a nucleophile uses its electrons to form a bond with an electrophile, what happens to the nucleophilic center, that particular atom, that nucleophilic atom, what happens to it will depend on its nature. If it is negatively charged, if it's a negatively charged nucleophile, after it has formed a bond with the electrophile, it becomes neutral. But if the nucleophile is neutral, it does not have additional electrons, when it forms a bond with an electrophile, in the product, that nucleophilic center, that nucleophilic atom will have positive charge. That's what we should know. Okay, so in here, this is a scenario. This is a reaction between this nucleophile and this electrophile. Remember, we have identified this to be the electrophile and this to be the nucleophile. For aminophenol is the nucleophile, while acetic anhydride is the electrophile. We have further identified the bond formation is between this nitrogen and this carbon, and this bond formation between this nitrogen and this carbon, it is this one which is the nucleophile and this one the electrophile. And then we went further ahead and said it is the nitrogen of 4-aminophenol which is nucleophilic, and it is the carbonyl carbon of acetic anhydride which is electrophilic. So this one will donate electrons. When this one forms a bond with it, like that, in order not to violate the octet of this carbon, a bond has to break. So it is possible this bond, this sigma bond could break, or this pi bond break. But the bond that is going to break will be the weakest pi bond. The weakest pi bond breaks, and the product is formed. This is a product that is formed. Of course, since the nitrogen, this nucleophile is a neutral nucleophile, when it uses its electrons to form a bond with the carbon, it becomes positively charged. So this nitrogen must become positively charged. And then here, since the electrons of this bond have moved, the electrons of the pi bond have moved to the oxygen becomes negatively charged. So this is a neutral nucleophile. When it uses its electrons to form a bond with an electrophile, this nucleophile becomes positively charged. Of course, the other atom, this oxygen, becomes negatively charged. So let's look at this. Look at this, very straightforward. When a neutral nucleophile uses its electrons to form a bond with an electrophile, this neutral nucleophile, since it has donated its electrons to form a bond with the electrophile, it becomes positively charged. It's given. And of course, when a bond is formed in here, in order not to violate its octet of electrons, the formation of the bond has to be accompanied by breakage of a bond. When this bond breaks, this oxygen becomes negatively charged. So the next rule is about conservation of charges. Charge, be it positive charge, negative charge, a neutral charge, is conserved in each step of a chemical reaction. Charge is never created nor destroyed. You remember in high school when you were balancing a redox reaction, in addition to balancing the atoms on both sides, on the reactant and the product side, you are also making sure the charges are balanced. If the charges in the reactant and the charges in the product are not the same, the reaction is not yet balanced. You have to still work on it to make sure not only the atoms are balanced, the charges are also balanced. So when you look at this, so this is neutral. This is also neutral. The reactants are neutral. Product of this reaction, this one, it must also be neutral, because charges can neither be created nor destroyed. So in here we have created charges. We have created a positive center and a negative center. but the product we have formed remains neutral. This +1 and minus cancel out. So this is neutral, this is also neutral. So when you are writing the mechanism of an organic reaction, you must take care of charges. You must make sure charge is conserved. Also trace where charges are going to be formed. So remember we said when you have a neutral nucleophile, when it forms a bond with an electrophile, that neutral nucleophile becomes positively charged. We should not forget. And then when a bond breaks like that, the electrons of this bond will go to the electronegative atom like this. We should not forget that. So what this basically is saying, reactants are neutral. The net charge in here is neutral. This is neutral. This is also neutral. The net charge on the product should also be neutral. Neutral reactants lead to neutral products. So there is conservation of charges. The charges are conserved. So net charge of the reactants should be the same as net charge of products. Okay, that's what step 8 is all about. You must make sure charges are conserved. Without conservation of charges, you've not drawn the mechanism of the reaction very well, because the charges at the end of the day will be involved in a chemical reaction. This intermediate we have formed, the fact that we have a negative charge on the oxygen and a positive charge on the nitrogen will determine how the next step of the reaction is going to be. So you should make sure that you indicate the charges. You also make sure there is no difference in terms of net charge between the reactants and the product. Net charge of the reactants must be the same as net charge of products. Let's go to the next step. So this is what we have. You remember, our focus is to form paracetamol and acetic acid. In paracetamol, we have a carbon-oxygen double bond here. There is a double bond between this carbon and this oxygen. So that carbon-oxygen double bond must be formed. So we'll use this lone pair of electrons and form a bond with this carbon. We use this lone pair of electrons and form a bond with this carbon. So when you form a bond with this carbon, if nothing happens, the octet of this carbon will be violated. If you form a bond with this carbon and leave it the way it is, because of this double bond, there will be 4 electrons in here, 5, 6, 7, 8, 9, 10. So when these electrons are used to form a bond with this, a bond has to break. So when these ones form a bond in there, a bond has to break. And then the bond that's going to break will be the weakest bond. The bond that's going to break is the one that can accommodate the negative charge. When a bond forms like this, either this carbon-nitrogen bond or carbon-oxygen bond or this carbon-carbon bond has to break. If this carbon-nitrogen bond breaks, we are going to get the reactants. Okay? We will not have achieved. So breaking that bond does not make sense. The two possible bonds that we have to break are this carbon-carbon bond and this carbon-oxygen bond. If you break this carbon-carbon bond, we'll have a CH3 which is negatively charged. Carbon that's negatively charged is very highly unstable. So that's not going to happen. So when this carbon-oxygen bond is formed, it is this bond between this carbon and oxygen that's going to break, so that when this bond forms, and then this bond will break, and then the electrons of this bond will go to this electronegative element, oxygen. Oxygen can happily handle electrons rather than carbon. So a lone pair of electrons from the oxygen forms the double bond with the carbon atom to which it was initially bonded to. Remember, initially we had a carbon-oxygen double bond in acetic anhydride. When the nucleophile attacked that carbonyl carbon, we broke this pi bond, because pi bonds are weaker than sigma bond. That's why the pi bond was broken. Now, to form the product, the double bond has to form back. When this double bond forms back, another bond has to break in order not to violate the octet rule. So subsequent to this, a leaving group must depart from that carbon. From this carbon, we have 3 leaving groups. It is this one that can leave, it is this one that can leave, or this one can go like that, or this one can go, this bond can break and then it goes like that, or this bond breaks for it to go like that. So which one is going to break? Is the bond that's going to break is the bond that has better chance of accommodating the electrons. So if you break this one, of course nitrogen can happily take the electrons and the electrons can go and neutralize it. But if we break this bond, we are going to get the 4-aminophenol will not have formed our product. In order to form our product, to form the product, it's either this bond or that bond that's going to break. But this bond will not break because carbon cannot accommodate a negative charge. But a very electronegative element like oxygen can accommodate electrons. So when this bond forms, it is this bond that's going to break. This bond breaks, forming these intermediates. So now look at these intermediates. In here, we had an oxygen negatively charged, a nitrogen positively charged. This is positive 1, this is negative 1. What is the net charge? 0. Even in the intermediate products that are formed, you see one of the intermediate is positively charged, the other intermediate is negatively charged. +1 and -1, neutral. At every stage of the reaction mechanism, the charges must be conserved. The net charge in the reactant must be the same as the net charge in the products. So these are the 2 intermediates that are formed. So now we have not yet formed our product. You remember in our product is paracetamol. On paracetamol, we do not have a positive charge here. So now these 2 need to react in the next step. These 2 will react. So how is going to happen? So now this one obviously is going to be a nucleophile, while this one is going to be an electrophile. Which atom do you think this oxygen is going to attack? Is it going to attack hydrogen or is it going to attack the nitrogen? Obviously, you will say it will attack the nitrogen because the nitrogen is positively charged like that. But if you remember, our product does not have a bond between this oxygen and the nitrogen. In our product, paracetamol is a product that does not have this additional hydrogen. So this one is going to use its electrons to form a bond with this hydrogen. And then when it does that, this bond breaks. The point I'm going to arrive at, despite the fact that physically the positive charge is sitting on the nitrogen, but the partially positive center, the more positive center in this bond is the hydrogen, is not the nitrogen. Because nitrogen is an electronegative element. Isn't it true? It is the 3rd most electronegative element. So it's not happy having this positive charge on it. So what it's going to do, this nitrogen will pull electrons from this bond. Most of the electrons of this bond will be taken towards the nitrogen, neutralizing the positive charge on the nitrogen. So when that happens, this hydrogen becomes positively charged. So this oxygen will not be attracted to the nitrogen. Instead, it will be attracted to the positive center in this bond. Let me explain it again. When you look at this molecule, you will see that the positive charge is on the nitrogen. Then you might think the bond formation next will be between this oxygen as a nucleophile and this nitrogen as an electrophile. Then you might go ahead and draw a bond from here to here. But that will not happen because this positive charge, even though it is physically seated on the nitrogen, it is really not on the nitrogen. Let me explain. If you have a bond between nitrogen and hydrogen in a neutral molecule, since nitrogen is more electronegative than the hydrogen, the nitrogen will pull electrons of the bond towards itself. As a result, there will be excess of electrons on the nitrogen and deficiency of electrons on the hydrogen because of the polarization of the bond. So when you put a positive charge on an electronegative atom like nitrogen or oxygen, they are not going to be happy about it. So what they are going to do, they will use all their power, pull electrons from their neighboring atoms in order to neutralize the positive charge that is developed on them. At all costs, they will pull electrons from the neighboring atom so that they become neutral. So what's going to happen in this bond between this nitrogen and hydrogen, under normal conditions, this bond is polarized. But now we have put a positive charge on the nitrogen. So what the nitrogen is going to do, aggressively pulls electrons of this bond towards itself. So electrons of the nitrogen-hydrogen bond will go to neutralize the positive charge that's developed on the nitrogen. When these electrons goes to neutralize the positive charge on the nitrogen, they are taking electrons away from the hydrogen. As a result, this hydrogen becomes positively charged. This is a case when you have hydronium ion. Hydronium ion is a hydrated acid. When H plus react with water, you get H3O plus, where oxygen being in the middle, we have oxygen in the middle, we have hydrogen, we have hydrogen, we have hydrogen, 3 bonds. The oxygen in the middle is positively charged. But H3O plus is nothing but an acid. So when H3O plus react with a base or with a nucleophile, the nucleophile is not going to attack the oxygen. What the nucleophile is going to attack is going to pick or attack the hydrogen, leaving the oxygen. Because the oxygen, when it is made to be positively charged, the oxygen, it withdraws electrons from the oxygen-hydrogen bond aggressively in the process, neutralizing itself, but making the hydrogens desperately without electrons. So the hydrogen becomes very, very positive. So a base goes and picks those hydrogen, a nucleophile goes and picks those hydrogen. So that's the situation in here. This oxygen now will go and form a bond with this hydrogen. So since this oxygen has got these additional electrons, it's going to use these electrons to form a bond with hydrogen. This oxygen as a nucleophile is going to donate electrons to form a bond with this hydrogen. So when a bond is formed between this oxygen and hydrogen, this hydrogen will have the 2 electrons it needs as a result of bond formation between the oxygen and hydrogen. If it does not detach itself from the nitrogen, this hydrogen will have 4 electrons, which is not allowed. So when this oxygen forms a bond with hydrogen, when this oxygen supplies 2 electrons to form a bond with hydrogen, the bond between this hydrogen and the nitrogen, this bond has to break. This bond will break, and the electrons of those bonds are not going to go anywhere. They are going to be on the nitrogen. These electrons of the bond will be on the nitrogen. Now, when the nitrogen gets additional electrons, the nitrogen becomes neutral. So this is how it is. This oxygen forms a bond with this hydrogen. So you'll have an OH bond. When you form a bond between this oxygen and this hydrogen, this bond breaks. And then the electrons of that bond will neutralize the positive charge. So you will draw another arrow starting from the bond pointing towards the positively charged nitrogen, like that. When it does that, you get paracetamol and acetic acid. This is basically the mechanism of formation of paracetamol acetic acid from 4-aminophenol and acetic anhydride. I don't know how much time I took to explain this, but when you put everything together, as I told you, the mechanism of this reaction fits very well in one page. So this is basically the mechanism. everything I explained in so many steps, in so many slides, fits in one page. So when you are required, when you are asked to show the mechanism of a reaction, the mechanism of reaction of, like for example in this case, 4-aminophenol with acetic anhydride to give paracetamol and acetic acid, these are the only thing you need to show. You do not have to explain in detail. The reason why I took all my time, explain the whole thing in detail in so many slides, taking a lot of time, is so that you understand the concept. Otherwise, if I asked you to show the mechanism of this reaction, this is basically what you write. So it is very important, probably you identify the nucleophile and you say this is the nucleophile, and then this is the electrophile, this is the nucleophilic center on 4-aminophenol, and then this is the electrophilic center on acetic anhydride. Nothing more. Then you just show arrows. An arrow, let's start from here, going to that. When that happens, this double bond breaks, you get this intermediate, and then this intermediate, it will form back the double bond. See this double bond was the one that was broken, then it forms back the double bond. When it forms back this double bond, this single bond between the carbon and oxygen breaks. The electrons of this bond will go to the oxygen becomes negatively charged. So you form these two intermediate, this one, and then this one, using its electron as a base or as a nucleophile. It forms a bond with this hydrogen. When it forms a bond with this hydrogen, the electrons of this bond break, and then the electrons of those bond goes to neutralize the positive charge on the nitrogen, giving us neutral paracetamol and acetic acid. I hope by now you have the skills. You have acquired the skills in proposing the mechanisms of organic reaction, be it polar reaction or radical reaction. I want you to feel confident that you have the knowledge and the background required to attempt to tackle most mechanisms of organic reactions.